We're going to assume in this video that you've already watched the video previously on sequences. So let's assume we already know what a sequence is. Just as a quick reminder, a sequence is just a list of terms. It's a function of n that's defined on the positive integers. So you get a function value at 1. We call it a sub 1. That's the first term in the sequence. And then a sub 2, then a sub 3, the third term, the fourth term, the fifth term, etc. These are not added. These are just individualized terms that you get from plugging in 1 or 2 or 3 into whatever function this is for a given sequence. What we're going to look at in this video is something called partial sums. Partial sums. So when we say the nth partial sum of a sequence, the way that's written is capital S subscript n, and this is what you get when you add the first n terms of a given sequence. So for this given sequence here, the nth partial sum would be taking the first term of the sequence and adding it to the second term of the sequence and adding that to the third term of the sequence, so on and so forth up until the nth term. So S sub 5 would be the sum of the first 5 terms of some given sequence, where S sub 10 would be the sum of the first 10 terms of a given sequence. We normally don't do that if it's just a sequence, but if you're adding them, then we change the name. We call it a sum. In this case, it's a partial sum. You'll see why we have the word partial in just a little bit. Now, obviously, this can get a bit cumbersome, if you're adding up 10, 20, 30 terms. So there's an alternate notation that kind of condenses things a good bit. It's called sigma notation, and it looks like this. We use the big capital Greek letter sigma, and we'll write, for instance, I equals 1 to n for a sub I. Now let me explain the way this works here. This is shorthand notation for this long string of numbers. You can basically think of the 1 as being where you start, and the n up here at the top as where we stop. Now you look at this and you might ask yourself, well Devin, why did you change it from a sub n like it was to a sub I? Well, I is what's called the index. I is going to be constantly changing. So for instance, when we plug in 1 as our start number, our beginning index number, you'll get a sub 1, a sub 1. And then the sigma notation, you can almost think of it as a machine that'll crank over from 1 to 2. And so we'll add a sub 2, so we'll let I be 2 instead of 1. And then we'll let I be 3, and then I is 4, and then I is 5, and we'll add and add and add over and over again until we get to our stop number, whatever that may be. We'll just leave it a generic n for now. So if you had the sum of the first 17 terms, you could condense that as the sum from I equals 1 to 17 of whatever that function is that generates your sequence. So it's a nice little notation there. All right, now something's pretty surprising about these partial sums. It turns out that if you take each individual partial sum, the first partial sum, the second partial sum, which is the sum of the first 2 terms, and then the sum of the first 3 terms, and get those results, that actually creates another sequence. It's not the same as the original sequence, but it generates another sequence. So this can get kind of confusing, especially when you're trying to differentiate between what's a sequence and what's a series or partial sum. It all gets a little confusing. So let me see if I can show you an example here to kind of help it make sense. So a sub n equals 1 over 2 to the n. That's clearly a sequence. It's a list of terms. As n changes, you would get a half, a fourth, an eighth, a 16th, a 32nd. That would be separated by commas. They're individualized terms. But let's check out the first few partial sums of that sequence. So S sub 1 would be the sum of the first term of the sequence. You just get a half. S sub 2 would be the sum of the first 2 terms of the sequence. So you get a half plus a fourth. Add those up, I think you get 3/4. S sub 3 would be the sum of the first three terms of that sequence. A half plus a fourth plus an eighth. Yes, that's a sum. That's a partial sum. When you total them, you get 7/8. Then next, S sub 4, you get a half plus a fourth plus an eighth plus a 16th. That's 15/16. But now check this out though. If you just look at each of the resulting numbers that you get out of these partial sums, you have S sub 1, S sub 2, S sub 3, S sub 4, and this pattern could continue. And those are a half, 3/4, 7/8, 15/16, etc. So it looks here like if you consider what the partial sums are, it generates another sequence. Now, is this sequence the same as the original? Absolutely not. But it's a sequence of partial sums, if that makes any sense. Okay, so now we have a good next logical step to take. The next logical step would be, okay, so if this is actually a sequence that you get from these partial sums, what would it mean if you took this out to infinity, if you found where it went as the n got larger and larger? So as the n gets larger, the limit as n goes to infinity of these partial sums, that would be the same as taking the sum not from 1 to some finite number, 1 to 5, 1 to 17. It'll be like taking the sum 1 to infinity, right? You're adding up all the terms, not just the first two terms, first three terms, first four terms. If you continue that for forever, you're getting an infinite sum. Now, since we don't have to stop at any particular place, I'm actually going to change the index letter back to n. That's usually the convention that we use. N equals 1 to infinity of a sub n. And that's what's known as an infinite series. We changed the name from sum. Sum is usually correlated with a finite amount. And usually when we use the word series, we're meaning an infinite sum. That's usually the convention there. So that's an infinite series. Now the big question in the whole chapter on sequences and series is going to be, does this infinite series converge? Does it add up to a finite amount? Now if you look back at this one up here that we were working on earlier, look at this series here. If you took the series, right, the series here from n equals 1 to infinity of 1 over 2 to the n. If you continually added these terms up, plus another, plus another, plus another, I think it looks pretty clear that yes, this will converge. You get 0.5, 0.75, and then something 7/8, a little less than 1, 15/16. That's pretty clear, the pattern, 31 32nds, 63 64ths. It looks like this will converge to 1. Now, we haven't seen that a rock solid proof of that. That'll come later. If you want to look at how to do this particular problem, you can watch the video on geometric series. It'll explain why this would be 1. But it's pretty clear just by our intuition that this would add up to a finite number. Now, clearly not all infinite series converge. Matter of fact, many of them do not. If you had the sum n equals 1 to infinity of, just take something simple like n, and you just continually add 1 plus 2 plus 3 plus 4, it just gets bigger and bigger and bigger. It's very difficult for a series to add up to a finite number, because the logic is you add more and more terms. It's very easy for that to grow and grow and grow to become an infinite value there. So there's certain criteria. Now it's very difficult just to look at a series and tell if it's going to add up to a finite number or diverge and be an infinite number. Some of them are so much on the fence post that you need a certain test. So if you watch the next video on an introduction to infinite series, we'll just kind of give a brief overview of each of these convergence tests for infinite series, and from there it'll link out to videos on all the different tests for infinite series, like the ratio test, the geometric series test, the integral test, the comparison test, ratio and root test. There's all sorts of tests, for given situations, they will tell you whether certain infinite series converge or diverge.